I hope everyone is fine. In today's video, we will be discussing about properties of asymptotic notations. Now, the first property is that we have order big O and omega, big O, omega as well as theta. We have been given that Fn is order of Gn. So then we can also say that A multiplied by any constant multiplied with Fn can also be an order of Gn. Let's say I say n is order of n plus 10. So I can also say that 2 multiplied with n can also be an order of n plus 10. So for that, we all know that 2n must be less than equal to c multiplied with n plus 10, and you can give any value of c to basically make sure this thing holds true. So for any value of n and c, this will hold true because technically n is order of n plus 10 anyways. Fine. So this is the first property. Second property is the reflexive property. Now, what is reflexive property? The very simple example that we can code is that if there is Fn, this can also be an order of Fn. Means any kind of complexity is an order of itself. This is one thing. If I'm writing that Fn is n square, so n square will also be an order of itself. So this is a very simple property, I guess. Then the third property that we have is transitive. Transitive means if Fn is order of Gn, Gn is order of Hn, then we can say that Fn is order of Hn. So this is another property that we can actually say that this is another property. It means if A derives B, B derives C, technically A is also deriving C. Fine. Then the fourth property that we have is symmetric property. Symmetric property says that if Fn is theta of Gn, then Gn can also be a theta of Fn. This is a very simple property, and this is holding true for theta notations only. This is a very important part that if I say Fn is n square, Gn is also, let's say, 2n square. So we can clearly say that n square can be greater than equal to 2n square. N square can be less than equal to 2n square. It holds true for theta notations also. So we can say that n square can be a theta of 2n square, and 2n square can also be a theta of n square. This is symmetric property. Yeah, we have already done the proofs of the same, so you can refer to the earlier videos regarding the same part. Then we have the next property, which is transpose property. And in transpose property, we have Fn is order of Gn, and then we can clearly say that Gn is also omega of Fn. This is as understood. We all know, let's say n is order of n square, then n square will always be omega of n, right? Because Fn, if it is less than equal to Cgn, so Gn can also be omega of Fn, where it is greater than value of any value with Fn. This is as obvious, because if Fn is n is less than n square, then n square can also be greater than n. So this is the case. Fine. Then we can do some additive operators also, like Fn is order of Gn. Your Dn, let's say, is order of En. Then we can say that Fn plus Dn is order of maximum value of Gn comma En. This is one case. So we are adding these complexities all together to basically have an order with Gn and En maximum value. Then last, not the least, we have another important part with Fn is order of Gn. Again, Dn is order of En. Then Fn multiplied with Dn is order of Gn multiplied with En. This is another important part. Hopefully, these all properties are clear. So thank you very, very much. If you like this video, kindly like, share, and subscribe. Thank you.